Right. Good afternoon, everybody. Thank you for coming along. And we're here to talk today about our experiences using BGP VPNs for edge cloud deployments. And obviously, we have to explain to you, it's a requirement, it's a legal requirement to explain to you what an edge cloud is. I'm sure you all don't know, and you really need to hear it again today, but never mind. And then we'll go through what we've done and the experiences we've had doing this. I have to say this is not a fix, right? We're not saying this is how it works, this is how it all works, we're all done here. What we're saying is that we've been taking an approach, and it's a little bit different from the way that other people have been doing this. Working with the OpenStack BGP VPN APIs, and we'd like to share that with you and see whether it's a model that would work for you as well, or how you feel about it. Feedback is welcome, but in the meantime, we'd also like you to explain to you how we see the world. So, to get on with the first part of this, obviously well, actually, before I do that, let me introduce my colleagues, or I'll get into a great deal of trouble. My name's obviously Ian Wells. I'm an engineer, distinguished engineer at Cisco, and I have Harish and Sebastian. They're the ones who've actually been doing the work, for what it's worth. So I'd like to point that one out as well. I just sit around and say, yeah, that doesn't look, but this is how it goes. So edge clouds, obviously, in a service provider, an edge cloud is really about just providing its VNFs out at comparatively the edge of the service provider network, closer to the customer than to the core of the network. And they want to do it for at least two reasons. One of them is, they obviously don't want to do it because it's actually quite expensive to do. You end up with a lot of edge deployments. But the reasons they do want to do it is it can reduce the distance between the customer and the endpoint. That can be useful from a latency perspective or a reliability perspective, for that matter. But it also is quite useful for reducing backhaul. So service providers spend a lot of money on fiber, and they spend a lot of money on and the things that connect to fiber, on the routers and the optics that go at each end of the fiber, and they don't like spending money. I'm kind of sympathetic on that. So if they can reduce the amount of traffic they send down a line, then that actually earns them money back. Money they're not spending, so they like that. But Edge Cloud also comes with a bunch of requirements. These are no more different for anyone else's Edge Cloud than a service provider in terms of being small in footprint. We're not looking at big clouds here. We're looking at ones that fit into a small rack somewhere, or smaller still, and reduce power consumption. So the fewer devices, as well as the smaller the devices, the better it all works out for people. And, quote, seamless integration into the service provider network. And that's where BGP VPNs come in. It's where MPLS comes in. Service providers use MPLS for various reasons, and they want to make sure that that their MPLS network is usable from these VNFs. These VNFs, to them, they're a virtual equivalent of a physical box they would wire into their MPLS network. So this has to work seamlessly for them to actually make sensible use. So why does it need to integrate with the service provider network? Service providers are really trying to use the MPLS to get cost efficiency out of their network. I think we've got a little bit more of that later in the presentation. But in order to actually get that cost efficiency, the attachment has to be, again, pretty seamless. This effectively is the virtual equivalent of the end of a cable that they want to plug into the virtual equivalent of a router. That has to be very straightforward. Again, the edge cloud is used in a number of logical locations. The logical locations are out at the edge pulling traffic in. Pretty common that they want to then run the traffic through an MPLS tunnel all the way back to the core of their network for it to go through a next site. Or maybe some of that traffic, drop off some of the traffic early and run the rest of it back. So service chains that span a network are, a thing that is desirable, shall we say, for service providers.
Right, yes. Cool. So the next part, we're going to talk a little bit about the actual service provider networks. So just to give a brief overview, what do service provider networks actually do? So the first question, I guess, is how do we actually reach destinations? So the service provider networks tell you the necessary information on how to actually reach your endpoint, your other site, through a service provider network. We have, with the WAN technology that we discuss here today and that are out there, they're usually defining an overlay and are independent of the transport that is used by the service provider network itself, where you have some kind of responsibility division so that you can actually control your own overlay, but the service provider is providing you the environment to do that. Especially more the newer technologies for SP-WAN have the capabilities to introduce multi-tenancy. That is something that is really relevant in our application here with cloud networking. And then in addition to that, most of these technologies also provide you with capabilities that allow traffic engineering, where you actually can define and optimize what you mentioned earlier, actually define how you want to use your service provider network and optimize its utilization. So just a brief overview of MPLS. MPLS is based on labels. It's a multi-protocol label switching. So it's basically using the concept of switching rather than routing to forward packets between endpoints in your MPLS cloud. And important here, it's not based on IP. It uses, in the underlay, it uses existing protocols or existing IP-based protocols to define the underlay and provide you the basis to actually operate properly. It is based on 3 different operations: the push operation, the swap operation, and the pop operation. Push means it's basically adding a label at the edge. Within the cloud itself, it's just looking at the label, deciding what to do, how to forward it, and maintaining the label and then swapping it out. And at the edge, where you leave the service provider, again, you're basically removing all the MPLS information. And at that point, it's standard IP again, and it's just forwarded to the cloud at that point. The question is, why do we actually have MPLS? Why couldn't we just use IP? So for SPs, it's important to make sure that they actually utilize their network properly, because whatever they do, it's expensive. They have to pull fibers, they have to use equipment, expensive equipment. So they want to make sure that all the environment is used to its optimal utilization. So another thing that they want to achieve with MPLS is the capability to use traffic engineering to exactly achieve that. So if you have a lot of flows with IP, you might run into a overutilization of certain links, whereby other links are completely underutilized. Now with MPLS and traffic engineering, you're actually able to do some kind of load balancing and optimization so that links are used equally and that you can actually achieve enterprise-grade connectivity across the WAN. The next section or the next WAN technology we're going to introduce is segment routing. Segment routing is an idea based on source routing. It's supporting 2 different data planes. You can either use it with MPLS directly, or you actually use it independent of MPLS with IPv6. In the world of IPv6, a segment label, which is the identifier that is used to identify different areas in the network and how you want to reach them, is defined by an IPv6 address, and in MPLS, it's actually, again, a label. So the source here is actually defining how you want to route through the network, how you want to reach your destination. It's defining the different segments to go through to get to your endpoint on the other side. An important concept here is that the actual state of the network is no longer within the network, but it's actually held within the packet header, because the packet header has all the information it needs to be able to reach the other side. Here, this is a brief introduction or brief overview of how that would look like. You come in on A and you have a set of IDs here. It's represented as labels or identifiers. Could be also an IPv6 address. And the underlying network or the segment routing network understands that it has to go through the segments of 100, 265 to then get out to the other side to reach the destination. Now, in addition to that, we also have eVPN, which is basically, again, an overlay, in addition, complementary to transport, to the transport layer. It uses BGP to define how to reach certain MAC addresses, certain endpoints through a MAC address. So it uses certain MAC address pairs, like MAC address IP pair, MAC address VNI pair, to say, okay, I have these endpoints on this side, I have these endpoints on this side, and BGP is advertising the information so that you can avoid things like a lot of ARPing across the network and overloading the network with unnecessary traffic that you can avoid by having eVPN. As I said, it addresses a couple of the shortcomings that we saw before with MPLS or other network protocols like network inefficiency, having to have different operational modes. And important here for our talk or the application in cloud is the lack of programmability that eVPN addresses, because it now actually can be very specifically programmed for endpoints with MAC IP pairs. Again, a short overview of how that would look like. One of the main advantages of eVPN is its capability to provide optimal forwarding using all the different passes it can have, ECMP. And yeah, so for example, here we show that all active multi-homing, single active multi-homing, so you can have different ways of getting to your endpoint by just specifying the endpoint information, and BGP is handling the remaining details. So the next section is why we actually want to use MPLS and OpenStack today, and what we currently have, what we use in our implementation, in our current design, and what we believe might be useful for the future. So conventional WAN edge models, this is a typical WAN edge where we have the PE under the control of the service provider. We have our border leaf, which is the CE, which is again under the control of the enterprise, or here the cloud edge. The handoff between the PE and the DC is defined by BGP mainly. And then the MPLS is basically defined from the PE onwards. So there's no MPLS information or MPLS capabilities within the border leaf. The cloud is basically unaware of what's happening further up north. So this is one of the implementations or possible implementations we have today with MPLS in the cloud, MPLS with OpenStack's BGP VPN API. The first one is the conventional model, what I just explained, where we have MPLS termination on the PE, and then everything below that is standard DC networking. With the MPLS over UDP model, what we do here is we encapsulate MPLS into UDP so that we can move the MPLS boundary from the PE actually to the virtual switch, and avoiding problems on the physical switch which would not understand the actual MPLS label. So that is what we do today. What we were thinking is going towards a more of an integrated model where we actually collapse the CE and PE capabilities into a single router, which we call a converged TOR, where we basically have the PE capabilities and also the CE capabilities, as well as being able to directly connect via L2 to the compute nodes. That way we are able to still have the MPLS termination on our converged TOR, but we now have direct connection to the virtual switch without having to go through another switch that is unaware of these technologies. So on the right-hand side, you can see what we implemented, what we currently use MPLS to the converged TOR with VLAN L2 further down south to the vSwitch, and then onwards to the VNF running on the compute. On the right-hand side, on the left-hand side, you see that we actually can do more than that. We can actually think of some other scenarios where we say, okay, what about moving the MPLS endpoint from the converged TOR down to the virtual switch? Now that we don't have any device in between that would cause problems, we actually can do that. And then even further down, we can say some of the VNFs might actually support MPLS. MPLS labeled, they understand what MPLS is doing. So we can actually move it even further down to the actual VNF that is running on the compute without having to involve any of the network elements in between. And then the model changes a little bit now, is where we have the converged TOR basically takes care of both the uplink, the northbound configuration where it talks to the service provider network, and is at the same time controlled by the cloud, where it's configuring the necessary information for each of the tenant networks to decide if it's going to an MPLS endpoint or not. So what we believe some of the benefits are is for what Ian already mentioned in the introduction slides, what is important here for the WAN edge or cloud edge is that we need to have a very small footprint, which means we need to make sure that we somehow can reduce the space and the power and the cost. And by collapsing 2 devices into 1 device, we're actually achieving that, because we now can use one single device to do multiple functions at the same time without having to rely on multiple devices. As you can see, as I discussed before in one of the slides, it actually enables, or there's a possibility to enable new capabilities that were not possible with other models before. And one of the things that now that we have more of a holistic view of the MPLS environment, because we have it end-to-end basically now, we can reintroduce things like OAM, for example, where we say, okay, we understand now that from the VNF all the way through the service provider network to the other side, we can have one picture without having to go through different entities, different responsibilities, etc. And that is the same thing with traffic engineering, where we basically can have converged traffic engineering from your cloud through the service provider network to the other side. So that's one of the elements as the responsibilities, where we basically say, okay, we on the P side, this is still under the control of the WAN operators. It's providing you as a cloud operator the information you need to be able to peer with the P side. But now the CE and PE side is under the control of the cloud. And there's some boundary where you say, okay, the P side is giving you the information you need to actually operate the PE, but everything else comes from the cloud operator at this point. So you're the one who's defining what to put into the network, with the exception that the WAN operator is still the one who's actually defining the necessary policies to make sure that your WAN is still working as expected and you have some kind of integrity. Otherwise, you would run into the risk of the cloud operator advertising IP addresses you don't necessarily want to have in the cloud or in the service provider network. Yeah, I think I hand back to Ian.
Right, so we've talked about if we change the model of hardware, if we change what we're controlling, we give ourselves a bit more power to actually do new and exciting things. But we're still working with the OpenStack BGP VPN API. It's a standard API. And obviously, an API is not its implementation. The API in the BGP VPN extension is deliberately designed not to say this is how it must be implemented, but to say this is what I want my BGP VPNs to connect to. It's trying to express intent. It's not trying to express the only way it can possibly be done. It does come along with a free bagpipe implementation of BGP VPNs. It's not the only way you can implement this. It's not even the only way that's out there. There's also an open daylight one. There's a Contrail one. But the question we've got here is whether or not those APIs are exactly the ones we want, or whether or not there's something that this shows that we could do that the APIs don't really let us do just a moment today. And I think the answer to that is no, it's not quite complete just yet, not for what we could do with this new model, because this gives us more possibilities than we had before. But on the other hand, we should be able to extend those APIs. They're a perfectly standard thing, just to make sure that it gives us the extra capabilities that we're looking for. And if we look at the models we were looking at previously, then this one here, this one on the right, on the left, is the one that's a problem. It's new and different. It's not one that we've ever discussed before. And it's not one that the BGP VPN APIs are really going to help us along with. So obviously that one is one that we're going to have to find new ways of describing using the APIs, something that fits in with the model we have today, but also allows us to describe this tomorrow. Another part of the modeling of the APIs between the WAN edge here is, well, to go through what we already have today, is we model a VPN as an abstract resource that we associate with a real resource in Neutron. So we say, here's a BGP VPN. It's got, root target. It's MPLS. There are a handful of things. A whole bunch of bits and pieces that detail how that VPN works in the wide area network. And then we attach it to something within Neutron. Now, once upon a time, that used to be nothing but a router. You could attach a layer 3 overlay to a layer 3 router. But we can also attach it to a network, layer 2 or layer 3 with a network. That's fine as well. And if we're being very, very sort of fine-grained, we can go all the way down to a port and say, this port's traffic will be immediately sent out over an MPLS or an SR overlay. So those possibilities all exist today. That's pretty good. We can do all of those with this model as well. Works about just the same. And the association's course define, as we've got here again. And the other thing that it allows us to discuss as we're making those overlays is we can have different kinds of overlays. So a layer 2 overlay is effectively a switch. It's well distributed. The actual ports are hundreds of miles apart, but it's a switch. So when I send something to a MAC address, I can trust that it will reach the right MAC address when it crosses the network. It's useful. It's more useful in DCI than it is in other places, but it is useful. And EVPN means that at least I've got some idea of where the MAC address lives, so I don't send packets in all directions hoping that eventually it'll arrive at the right direction. Layer 3 overlays are a very common thing. This basically looks like, within a wide area network, it looks like I've got my own magical routers that work just for me within the overlay. So I send it to my next hop in the overlay, and it will eventually find its destination. That's nice and easy, very service provider compatible, very much the model of the world that they think in terms of. But a kind of overlay that you can also have is a point-to-point overlay. This is effectively a cable with 2 ends. Again, hundreds of miles apart, but it's only ever going to have 2 ends, so I don't need to think about where I'm sending the packet. It will always go in that direction to the guy over there, because that's the only other end to the cable. It's really useful, as it turns out. It's really useful to define things like service chains. Service chains, we talk about service chains as if they're magical and exciting. But they're often quite boring. They're often basically VM, link, VM, link, VM. That's it. Just beads on a string, if you like. But it's a reasonable thing to want to basically chain something out on the edge to something further in. It's a perfectly normal thing to want to do, but that chain is obviously stretching over hundreds of miles. If we can define point-to-point overlays within the BGP VPN APIs, we can do more things than we can do before, and we can do them more efficiently. However, I would say that changing APIs is hard, and agreeing APIs is also pretty hard. And agreeing APIs in the face of no evidence whatsoever is really very hard indeed, because it just basically involves 2 people saying that'll never work with no evidence whatsoever. We went through this quite honestly with the BGP VPN APIs the first time. We were trying to agree them for the longest time before Thomas Moran actually sat down and basically implemented something and said, look, this works, so these APIs are good now. And I think that's what we need to do here as well. We want to do some more experiments with the implementation before we actually go and say these are the APIs we should have. But we are, we're pointing in the direction of where we think the changes are coming, but we will get the detail done before we basically jump in and say we've solved the world's problems. So watch this space and we'll keep you updated as to what we learn.
Let's talk a bit about our implementation. So what we're saying here is that, as Ian just mentioned, there are a definite set of requirements which we are working on. So as you know, when we talk about edge cloud, it's a finite amount of space which we are thinking in terms of what the actual location will look like. So we are basically talking about something like a half closet space, something between 4 to 6 RU. That means that every RU of networking gear which we put there has to be effectively utilized. Many of the customer requirements in this case is to make sure that if you are putting gear there, put it to the best use as possible. So if you are putting an existing top of rack over there, ensure that we can get the maximum out of it. And since we always have to put something anyway in a fully redundant fashion, at least 2 RU is spent on that. That means that they were asking us something whether we could actually, can you give us a router which can do a switching or a switch which can do routing so that we can actually fully utilize that. So a model which we had been trying to see is whether we could actually move the provider edge down to the TOR itself. So we happen to have a few big toys in our lab which can actually do something like that. That means that it's just a matter of trying out whether this is a feasible solution with the API which we have got at this point. Now, in terms of implementation, what it means is that we didn't need to actually change the model itself. We still run the API itself in the Neutron Neutron server in the controller space. What's different now is that we can have our provider actually, instead of running a separate BGP speaker, just write a configuration to the TOR to make sure that it's a full-fledged BGP speaker. And since we have been running this sort of stuff out for ages, we have probably a pretty good BGP stack out there which we can fully leverage with that. What that means is that the Tor itself can be both a control, running both the control plane as well as the data plane. And what this means is that any traffic which needs to go out to the WAN could be encapsulated with MPLS right at the Tor itself, and the rest of the components doesn't need to be modified at all. I will still say that this is only an evolution. This is one of the things which we could actually do at this point with what we have. What Ian has been talking about with respect to bringing down the data plane all the way to the VNF will be a little bit more work to be done with respect to that. But the fact that we can control the Tor, or we actually have some ability to do that, make sure that we can make the Tor as a full-fledged LSR, even when we actually try to move the VNF all the way down to the VMs themselves. A little bit about implementation. Of course, we have a little bit bias towards networking VPP. I mean, Jan is one of the authors and I am one of the maintainers, so we are more familiar with it. So that's something which we can actually try to use to get something quickly rolling out. But we don't think there is any restriction with respect to any other mechanism drivers or backends itself. The API and the fact that the API is completely separated out from the backends itself gives us fair amount of flexibility. What we have been, one thing which we wanted to leverage from networking VPP was the fact that it uses an intent-based model. What that means is that instead of using a control command to tell the agents to do something, we just publish the desired state to our key value store, which is etcd now, and means that we run a group of agents who can essentially figure out whether this is something they need to act on, and depending on that and the data already available there, they can kind of self-configure themselves. This gives us a lot of flexibility in terms of what we can actually incrementally evolve. So in the beginning, we were trying to run a bit of an addition for the BGP VPN provider itself, and tried a bit of something to run a PE agent. So this is an agent which can essentially understand the intent of the API commands, and depending on who it's programming, try to translate that to the required one. So we can actually run these agents both independently in the controller, and in this case, to even try to run directly in the equipment or the top of rack itself. In that case, one of the benefits we get is that we don't need to actually make sure that we don't need to register the TORs as the OpenStack doesn't need to know the TORs as pre-configured. They can kind of self-identify that there is some work to be done and kind of automatically program themselves. This means that without making further changes into the provider itself, we can actually add additions to the existing L2 agent or a mechanism driver and kind of bring in the functionality down to the compute nodes too, without they just need to be understanding who is configuring what. A bit of implementation detail is that in our case we were essentially using netconf yang models to program the Tor and using gRPC as the communication protocol to do that. How this the API translates to configuration is, some of you might be familiar with this, some of you may not. What it means is that when you create a tenant network, that essentially gets mapped down to an EVPN, EVI, and a bridge domain in the top of rack. And the initial creation of the VPN doesn't has any implication. What makes a change is when you create, for example, in the case of an L3 VPN, if you create a router, that gets translated to a VRF on the top of rack, and attaching a tenant network to a router essentially means creating a BVI or a bridge virtual interface on the top of rack and associating that to the VRF. And finally, when you want to actually attach your network or a router to the VPN itself, means you essentially are configuring your RTs and RTs in the BGP session and making sure that your VRF actually knows about that. So this is just a quick example of how you might do this with a popular router in this case, but this is just a matter of how your agent or whoever is programming it needs to translate, and these are already well known. In summary, we have tried to play with this. We had pretty good success with it so far. We think we can take it out a little bit and want to get more feedback or understand whether how this model will work with the biggest picture of OpenStack and the way we do things here in Neutron. Yeah, I think, yeah, that's, you want to conclude, Ian, or?
If you want.
Not sure, the next slide didn't come. No, okay.
Okay. Oh, you haven't done that. There we go. Yes, and actually this is, as Harish says, the conclusion of the talk. Obviously, one advantage of working for a rather large network equipment vendor is we have a lot of toys in the cupboard. You'd be surprised how difficult it is to get into that cupboard, but once you've opened the cupboard, it's good fun. So we got to play with this. It's not everybody gets to play with hardware and see what you can do with MPLS VPNs with a little bit of router programming at the same time. But it's our opinion here that this is something that we can do, and something that's actually pretty easy to work with, that can expand the APIs beyond what we can do today and give us a lot more flexibility in clouds. And when we're doing service provider edge clouds, that's quite a lot of power. So that's what we're going to try and do, and then we'll bring the APIs back out to the OpenStack Foundation, and anyone else can implement the same thing with whatever equipment comes to hand for them as well. And really, at this point, it's over to you. If you've got any questions, if you'd like to ask us about the implementation, or if you think we should be doing something entirely different, I'd like to hear it.
So let's assume I were deploying a single cloud today, but down the road I'm looking at having edge sites, multiple sites attached through BGP VPN. Do you have any advice for topologies or specific technologies that I would implement in my single cloud today to prepare for that down the road?
I don't think there's anything that you really have to do in the way of forward planning. Obviously, if you're planning on doing it in this model, then obviously you stick a router on top rather than a switch. That solves the problem. You can always redeploy your cloud later on, but that usually makes people cry, so that's your choice. Yeah, I mean, the other thing about this is there are a variety of MPLS topologies that you can use, depending on what you're up to and what, again, your company's preferences are. But this should work with anything from a mesh on upwards, really, as far as it goes. There's nothing that it's not capable of. We're down at the low level of MPLS. Choices in terms of implementation topology are basically up to you at that point. So I think you'd be pretty flexible from the outset.
So hello. Do you have, you mentioned before the service function chaining, so do you have any specific implementation, or did you test it, that you have one service function in one data center and the other service function in the other data center, and those belong to the same chain and they communicate?
Yeah.
I don't know.
So
Thanks.
service function chaining is a divisive topic, or another way of putting it is when two people talk about service function chaining, they're actually talking about different things and they haven't worked it out yet, because no one seems to be able to agree on what it means to them. But in the experience that I've had of people implementing this stuff, more often than not, again, it's beads on a string. You're not looking. Service chaining can mean things like load balancing, which for what it's worth is available in MPLS. So actually you could work with that. You can work with simply any cast addresses as you advertise it out within your routers. Or it can mean something like NSH, where actually what you're trying to do is run a service chain, which is really, I've got 10 VMs, and depending on my customer, it will go through 5 of them, and they get to choose which 5.
Yeah, NSH is aware of NF, so...
True enough, but interestingly, when you start looking at SRv6, it has another model for that. You can do, at the front, when you decide the segments that you go through, some of those segments can actually be network functions. That's a permitted model. It's an expected model in SRv6. So you can actually string together arbitrary chains of VNFs using SRv6. So there are some models that work for the complex, but for the simple, where I'm just saying ABC, in much the same way that works in OpenStack today in Neutron, and people tend to forget it, you don't need the SFC APIs to make magic happen there. That works today in this model as well. It's very straightforward. The more complex things, bring me your use cases, quite honestly. I'd like to hear what you're trying to accomplish, but it does seem that there's not a lot of common patterns out there for this at this point in time.
Okay, so let's say that we're actually using, I don't know, SDN controller to do NSH, to do service function chaining, and we're using NSH protocol. Okay, so...
Yeah.
So, is it possible to actually, I don't know, do you have any metrics, or did you ever implement that to have one service function in one OpenStack environment to one data center and the other service function to a different data center?
We haven't done NSH-based experiments for this. There are models that you could support it gets interesting because if you're looking at NSH as your option, then your switch needs to be NSH aware.
Yeah.
And there aren't any definitions of NSH awareness in OpenStack today. There are no APIs to program that. There's no clarity on that. So exactly how you take that forward, I think, would be difficult.
OVS speaks NSH in
Yeah.
user space and kernel space, and Open Daylight also speaks NSH with OVS.
Are there any OpenStack APIs to program Open Daylight to tell OVS what to do?
Yeah, the network SFC.
And that actually talks NSH nowadays?
Sorry?
That talks NSH
Yeah.
nowadays. Okay, my mistake. Then, in any case, I haven't tried it, so you can
Okay.
probably tell that much. But I wasn't aware that had NSH built in, but thank you for that.
So I was wondering if we could get your opinion on like that one specific subcategory of what he's asking around the point-to-point. If I've got autonomous control planes in each one of these like self-contained edge clouds, how do I abstract my model for said point-to-point or service chains or whatever if I want isolated control planes?
So what we try and do here is well, the first thing I'd say, and I happen to know you work for a service provider, so you're probably well aware of this, is that in service providers, you've got operations teams for the backbone network. And clouds tend to have teams of their own, independent, both engineering and operations, even when they're doing network functions. So it's important for us to kind of realize that these two things are interoperating as friends. No one has control over anything else. They have to come to common agreement. And that pretty much means that you have some sort of orchestration layer above the two. So something either tells the WAN what to do or asks the WAN providers what to do, depending on what your WAN operators what to do, depending on what you're up to, and then deals with telling clouds in multiple locations how they are to be using the WAN. So if I'm trying to do a service chain of 2 or 3 locations, I would be telling the clouds, I would be giving the clouds coordinated messages about what they should be doing. So none of the clouds necessarily know about the other clouds involved, but they're all told to do one part of the job, and together the whole thing comes as a cohesive whole. So you need orchestration in this model. It doesn't work without somebody coordinating. Okay, I think we've done with the questions, so I'd like to thank you all very much.
Thank you.